algorithm, the random seed, etc. And so if information isn't really being created as suggested by classical information theory and algorithmic information theory, then what is AlphaZero actually learning? And this is something that we wanted to understand. Okay, so to resolve these questions, we propose Epiplexity, which stands for epistemic complexity. It's intended to provide a foundation for thinking about how we should select, generate, or transform data for learning systems. It measures the structural information that a computationally bounded observer can extract from data. In particular, it's the information in the model that minimizes the description length of data under bounded computation. And we'll unpack that a lot throughout the talk, so don't worry if that's hard to parse immediately. But intuitively, you can think of this as saying, suppose we have a model which is a good compressor of data. It's a good model. We're following all the prescriptions that we've learned in terms of Occam's razor, et cetera. Assuming we have such a model that's good at compressing data, what data should we show the model such that it's as incompressible as possible? And the reason that we might want that is because if the data is leading to a model that's fairly incompressible, but it's a good model, it's a good compressor for the data, then it might be teaching it structural information like shared circuits and subprograms, et cetera, that could be recycled in all sorts of other downstream settings. And it's very hard and a bit uncomfortable, I think, to reason about out of distribution generalization because, by its nature, we don't really know anything about this distribution. We're having to make predictions. And so it's just impossible to provide some kind of guarantee that the structure we're learning is going to be relevant to some specific distribution that we might have to consider. However, if we are able to extract a lot of predictable information content from a particular source of data, then we have a better hope that that representation can be recycled to a larger array of different settings. And this is something that we do observe empirically, and which we'll discuss more in a moment. To unpack this distinction between random information content and structural information a little bit more, we can look at the first row here, where in the middle column, we have just a simple gradient of color. And on the left column, we just have simple repetitive code. And so this is very learnable, but it doesn't really contain very much information. And so this would have low epiplexity and low random information content, which we're calling entropy here. As we'll see in a moment, one heuristic for measuring epiplexity is taking the area under the training loss curve above the final value of the loss. And so here, the loss just shoots down very quickly. We have low epiplexity, low time-bounded entropy. In the middle row, we have natural images and relatively structured code. This kind of data will contain a lot of useful information for learning a representation that can be applied in various different downstream settings. The loss will decrease more slowly, but it will still decrease. And we'll end up with a representation that has higher epiplexity and maybe moderate time-bounded entropy. In the bottom row, we just have white noise and random hashes, et cetera, things we have to memorize. And so the loss actually won't decrease very much. And so when we look at the area under the loss curve above the final value of the loss, we have low epiplexity again. We're not able to extract very much structural information content, and we'll have high time-bounded entropy. And so the time-bounded entropy is the information that's kind of unpredictable from the perspective of the model. And the epiplexity is the information that's predictable from the model. But if there's a lot of epiplexity in the data, it's going to be hard for the model to learn that structure. And so if you see sustained and substantial decreases in loss, that would imply that a lot of information is being transferred from the data to the model. And we call that information epiplexity. And it's very important to consider this from the perspective of a time-bounded observer. Going back to, for instance, this example of pseudorandom numbers. So if we just look at white noise that's been generated using pseudorandom numbers, if we have an unbounded amount of compute, this is actually deterministic and it's predictable. But to most observers, it's very unpredictable. So this is an observer-dependent measure of information. And this might be a philosophical aside, but one can debate about whether we want absolute measures of information, like Shannon information and Kolmogorov complexity, or whether we actually want observer-dependent measures of information. And my contention would be that if we want to reason about the properties of a learner, then these definitions should be specific to that learner. Okay, so let's back up a little bit and talk a bit about the history of information theory and to some extent learning theory, and then we'll dive into the details of epiplexity, its definition, and how it can be applied. Okay, so there are many different measures. In classical Shannon information theory, information is the surprisal in seeing the value of a random variable. Algorithmic information theory develops later, also applies to non-random variables and often measures the incompressibility of data. Intuitively, useful information should reduce our uncertainty in predictions. So in Shannon information, if we have a random variable capital X with distribution P of X, the information of an outcome drawn from this distribution is log base 2 of 1 over P of X measured in bits. And so this measures essentially how surprised we are in observing X. If we observe a sample that's low density, we should be very surprised and we gain a lot of information. The Shannon entropy measures the average information content in X, and the mutual information between X and Y measures our reduction in uncertainty about X after having observed Y, or vice versa. And so Shannon information has several key properties. One I've already briefly alluded to, called the symmetry of information. And so this says that the information in predicting X from Y is equal to the information in predicting Y and then X. Deterministic transformations don't add information. So if we have a deterministic transformation F such that Y equals F of X, then the entropy of Y given X is 0. And as a corollary, the entropy of F of X is less than or equal to the entropy of X. So we're only losing information by doing these transformations. Yet we know that they're very, very useful for training our models. And then we have the data processing inequality, which is quite related. If Y is obtained from X through some processing, could be deterministic or not, and similarly Z through Y, then the mutual information between X and Z is less than or equal to mutual information between X and Y. And according to Shannon information, objects which aren't random don't contain information. Okay, so then there's algorithmic information theory, which applies to any object X. It doesn't have to be a random variable. In algorithmic information theory, the prefix Kolmogorov complexity is the shortest self-delimiting program that outputs X and then halts. So you can think of this as kind of the best possible compression of X. It also has a symmetry of information property and an information non-increase property like Shannon information. And like Shannon information, it's also an absolute measure of information. And it doesn't separate useful information from unpredictable structure. It's impossible to compute the shortest program that generates X, but we can often upper bound it. So we can measure the file size of our model after training, et cetera. And that can still be useful. So we've made use of Kolmogorov complexity quite a lot in formulating generalization bounds for trying to understand scaling law behavior. And to some extent, that actually inspired this work on epiplexity. So I don't want to say that these quantities aren't useful. They actually are very useful, but there are big open questions. Like, could we use Kolmogorov complexity, for example, to separate useful information content from just random noise? And quite often the answer is no. This is something that has been considered. So there's something called sophistication, which is the smallest Kolmogorov complexity of a set S such that X is a random element from that set. So this does try to carve out structural information from random information. Unfortunately, it's difficult to find high sophistication objects due to something called Chaitin's incompleteness theorem. So we can't prove that the Kolmogorov complexity is bigger than some amount typically. And due to this assumption of unbounded computation, quite often complex objects appear to lose their complexity when measured by sophistication. So we could think of something like alpha 0 again. If you don't account for computation, then you could run millions of TPU hours on some kind of simulation, and that's not really accounted for in trying to measure what's been learned by this system. And it's not easy to just make sophistication time-bounded. In the paper, we show it becomes basically constant for all strings. And again, sort of our key contention is that understanding the role of computation is going to be really central for trying to make sense of things like emergent phenomena and the value of synthetic data. Finally, there's also something called Levin complexity, which is a compute-limited notion of Kolmogorov complexity. So it's concerned with how compactly you can generate one specific output rather than what can be extracted from a distribution. Pseudo-random numbers would still be treated by Levin complexity as simple because there's a short program that can generate pseudo-random numbers. It doesn't take a lot of time to run. However, as we've discussed, there's no learnable structure if we have polynomial time compute constraints, and this again doesn't distinguish between unpredictable and predictable structure. Okay, and we can also question what it means for something to be random. This has been a question of great interest to mathematicians and philosophers for quite some time. In the mid-20th century, mathematicians were really interested in formalizing a notion of what it means to be random, and they were often considering uniformly sampled binary sequences from which we can construct other distributions. And this leads to a number of really interesting questions, like are all sequences equally random since they're equally likely? So we could consider a sequence of just ones or some sequence like 1, 0, 0, 1, 1, 1, 0, 1, etc. And if we compute statistics of these sequences, the law of large numbers would say that the average entry should be a half, which clearly doesn't apply to this first sequence of ones, so it does feel like something is missing. And there are other notions of randomness, like Martin law of randomness, that try to address this instinct, saying, for example, a sequence must pass all computable tests. And then there's a notion of cryptographic randomness, that sequences must pass all polynomial time randomness tests. So in cryptography, they've thought quite a lot about computational constraints. There are notions like one-way functions and so on, which are easy to evaluate in one direction, but very computationally expensive to invert. We have not thought that much about computational constraints in information theory and learning theory. Okay, so pseudorandom numbers, we've sort of touched on this a little bit. This is just a formal statement of what we've been saying, that they're indistinguishable from actual random numbers if you have only polynomial time compute. And here we have a definition of a one-way function. So we can compute the Shannon information and algorithmic information of pseudorandom numbers and show that you don't gain any information, you only lose information through these deterministic processes. And as a final piece of background, we can consider elementary cellular automata. So these are a really nice way of starting to try to make sense of some of these questions. So you've probably heard in passing of something like Conway's Game of Life and so on, and this is related to that, and it's really quite simple and I think worth understanding. So elementary cellular automata, or ECA, provide a good mechanism for reasoning about the role of computation in deterministic transformations. In their simplest form, they're just a 1D array of binary cells, and then each cell's next state is determined by its current state and the states of its two neighbors. And so since these are binary cells, that means we have 8 possible local neighborhoods here. And then we can assign a rule to each of these local neighborhoods. So that means we have 2 to the 8 or 256 possible different rules. And some of these rules give rise to very sophisticated structure. We almost have like random number generators. And then some of the other rules are very simple. So here we basically see time running from top to bottom in the evolution. And here we have an example of applying these rules. So if we have 1, 1, 1, we go to 0, 1, 1, 0 to 0, and so on for rule 30. And so for rule 15 here, we see very simple structure. For rule 54, we see sophisticated, but actually fairly predictable structure. You might not be able to just look at it and be like, that's predictable, but maybe if you look for long enough, you would think that. And then we have rule 30, which is effectively random, even though it isn't random. This is all deterministically generated, just like pseudo-random numbers. Superimposed on these images, I have these pictures of coffee and cream. And so part of the inspiration for this work also came from a blog post by Scott Aronson around 2010, where he was considering a system of coffee and cream, which were initially separated. And then he was imagining that as you mix them together, the entropy of this system is gradually increasing, but the intuitive complexity of the system seems to be kind of non-monotonic. It increases and then it again decreases. At the end, everything is just kind of random and uninteresting. And so for quite some time, there's been like a quest for some sort of quantity that would capture this intuition and help us explain the value of data. And so we can map each of these states onto these ECA rules. We were also motivated by a lot of the work that we had done in pre-training LLMs for one problem and then applying them to very different seeming problems and finding surprisingly that it could work very well. So we had the first paper using LLMs for time series forecasting. And in some sense, this wasn't even really meant to be a paper. So this was before ChatGPT. And we were just kind of curious, like, what would happen if we just naively like fed time series represented as strings into GPT-2, GPT-3, and have it extrapolate the next sequence of string tokens. And we didn't necessarily expect this to work at all because these models had been pre-trained on just next word prediction, and we weren't updating them at all. And we saw that in some cases, they actually worked better than purpose-built time series models that had been specifically trained on that time series data. And so in a completely zero-shot capacity, a model trained for next word prediction was working better at doing time series extrapolation than purpose-built time series models trained on time series data, even the training data for these problems where we're doing in-context learning and prediction. And so we really wanted to understand these kinds of results. We had a similar result in generating stable inorganic crystals. And so here again, we had an LLM trained to do next word prediction, and then we had it generate crystals with various properties we wanted to select for. And this also seemed to work better than purpose-built models for this application domain. And the chemists we were working with were like kind of shocked throughout the project. It was really an interesting experience. In this paper, we did do fine-tuning. So we represented locations of atoms and energies as text and fine-tuned. But I gave a talk about this a couple of years ago at the Flatiron Institute. And someone came up to me after the talk and said, we read your paper, and actually we found out how to get rid of the fine-tuning. So it's all just zero-shot language pre-training, and it works just as well. And so this was kind of mind-blowing as well. And there's also this result, not from our group, recently about how something called neural cellular automata, quite related to the elementary cellular automata we were just discussing, can be used as pre-training, et cetera, for all sorts of seemingly quite different problems like code and math, et cetera. And so where does this transferability come from? And in our papers in the top row, we did have some reasoning about that. About half the time series paper was trying to understand what was going on, but it also felt like there were just missing foundations for thinking about these questions. Okay, so let's get into those foundations. Here we have the formal definition of epiplexity. Hopefully now you've had enough time with the intuition that it doesn't feel very scary. And it's not very scary, even though it's a lot of words and a few equations. Epiplexity is the size of the model that minimizes the description length of the data when searching over a space of time-bounded probabilistic models. So the description length of the data can be written as the model bits, so like this bar P plus data given model bits. And so that's the second part here. And so first we find the model that minimizes that under computational constraints. And so that's just determined by us, the number of parameters, the number of data points we're training on. And then once we found that model, we measure the size of that model. So we call that the epiplexity. And then the remaining part is the time-bounded entropy. And so you can view this as like a validation loss-like term. This is the amount of structural information that we're able to extract from this distribution. So I'd also like to note that this is a distributional definition, so it's different than Kolmogorov complexity. Okay, so there are several ways that we can try to measure epiplexity. The simplest, as I mentioned, is looking at the area under the training loss curve above the final value of the loss. So this is motivated by something called frequential coding and information theory, where the intuition is that if you have this sustained and substantial decrease in loss, then there ought to be a lot of information transferred from the data to the model. And you can use the dynamics of training to understand the implied code length of the model that you're training. And so you can use entropy coding to basically derive this, and you end up with something like this area under the loss curve. Yeah.
Does this decomposition only make sense for negative log likelihood?
The question was whether this decomposition between the baseline, you
mean equation 3 or?
I'm looking at the plot, right? Bottom left. So we're thinking that the loss is going to converge to some value, and that is our asymptote, right? So we're measuring all of those time-dependent quantities on top of that loss as the difference, the area under the curve on top of that dashed line.
Mm-hmm.
So does this kind of decomposition mostly make sense for negative log likelihood because of its connection to entropic quantities, I guess, information theoretic quantities?
I think the answer is mostly yes. I have a derivation for this at the end, and so we could return to it and think about how it could generalize, but I think essentially yes. Yes.
Thank you.
Yep.
I actually have another quick question. What if there's many models that satisfy this this argument in equation 3?
So ties are just broken by the smallest program. One thing that's important to keep in mind, I guess, is that this frequential coding approach is just a way to approximate epiplexity. It's not epiplexity itself. And we propose better ways to approximate epiplexity in the paper, so something called frequential coding here. Another thing to keep in mind is that epiplexity is only something we want to measure for like the optimal compression, kind of the optimal model. So I think when people are first starting to parse this area under the loss curve idea, it's easy to think of like, oh, what if I use some crazy learning rate schedule or did something else to kind of like increase the area under this loss curve? Would that mean that like I have high epiplexity, but this isn't useful? The answer is no, because that would not give you a model that's like an optimal time-bounded MDL model. I guess, yeah, if you had several models that did this, then I mean, in practice, I think that would be kind of impossible to get exactly the same thing. You just tie broken by the smallest program, you multiple smallest programs, then yeah, I'm not sure. So there's also something called sequential coding, and we can talk about this a bit at the end of the talk if there's interest. Which, oh yeah.
I have a very basic question to better understand. I don't understand why you have this. So if you had talked about the minimum length program, I would have understood that. But why do you have the entropy term?
What I have this last part?
For equation 3, why do you have the entropy term in there as a part of the complexity measure?
Yeah, so this is kind of the amount of bits that are required to store the data. So this can decompose using the 2-part MDL code as the model bits plus the data given the model bits. And so that second part is the data given the model bits. And this can be viewed as kind of like a cross-entropy loss-like term. Yeah. Mm-hmm.
Sorry, just last question. So the expectation there in the negative term with the probability of the program, right? That expectation is based on the same distribution of the program, or is based on the data distribution? That is not necessarily the P star.
It's the data distribution.
Okay, so that is exactly the number of bits that you need know in the model to encode in average that thing. So how does it connect with universal source coding? Because in universal source coding, we do basically the same.
In what coding?
Universal source coding. In information theory, what we call universal source coding is when you compress a source without knowing the distribution of the source. And so you learn the data distribution with a block length. So here you don't have a block length because nothing grows up. You have just one data. It could be a data set, it could be one sample, it could be whatever. But basically, we're looking exactly to the same quantity. So, I mean, I was wondering whether you tried to connect this or not to universal source coding, but it's basically very much related. It would be interesting if you didn't to look at that. Yeah.
Yeah, it's a good question. We may have discussed that. We probably did discuss it in the paper, but I guess my main reaction is that there has been work on, of course, a lot of work on MDL for model selection. I think one of the key differences here is that we're not so interested in model selection. We're instead trying to reason about data selection. And so what we want in the end is actually to choose data that will have high epiplexity, will be as incompressible as possible, with the idea that maybe we're learning more that could be useful in various different downstream settings. And so, I mean, it might be possible for someone to look at this equation and think, oh, we have MDL, and we could have time-bounded MDL, and sure, yeah, we are trying to minimize the time-bounded MDL in order to measure epiplexity. But I think one of the kind of really fundamental distinctions between what we're doing here and what is typically being kind of considered in these kinds of contexts is we're not trying to reason about model selection, we're trying to reason about data selection. Yeah.
Okay, so you don't really care about the P star itself, mostly about the quantity, the value of this measure in equation 3.
And its properties, I guess, with respect to things like the symmetry of information and so on, once you have time bounding.
Thank you.
Yeah.
Sorry. I might be getting ahead of myself, and maybe you'll explain this in a second, but
Sure.
when you're going to approximate this kind of time-bounded size of the program with sequential coding, do you do that by making the learner be regularized somehow? Like, how do you bake in the fact that the learner is somehow bounded in how much it can learn?
Absolutely, yeah. So first we specify a time bound, and this is something that, it's flexible. It's basically whatever we would want to do when we're training this model. And so we had a heuristic which was based on the number of parameters and the number of data points it was being trained on, but this is, just whatever would be sensible for how you're going to be using this model. And then secondly, we did a sweep over hyperparameters. So this is to sort of show basically this Pareto optimal frontier, where we want the best time-bounded entropy for any given amount of compute that we want to expend. And once we've done that, we measure the area under the training loss curve. And so we basically just put our best effort into finding the best time-bounded MDL model through a hyperparameter search, and by doing everything we can in good faith to specify our model in a sensible way. And then we measure this area under the training loss curve.
Sorry, not to belabor this. So in the plot A, this is a learner that, as it's sort of iteratively learning, it is regularized somehow, right? Like it's not allowed to learn the biggest model it possibly can. It's somehow regularized to be small, either in number of parameters or
Absolutely.
processing time or something.
So it will be for a model that is like the best time-bounded MDL representation. And so for any amount of compute, we can try to estimate like the time-bounded entropy and the epiplexity. And then, so this area that we're measuring under the loss curve would be for a model that is kind of optimally specified from that perspective. And so it would not be for a model that is making like bad predictions, for example, on out of sample points, because then you would have very high time-bounded entropy and you would have high MDL for that model. Yeah, and so we also propose something called sequential coding, which is a much more rigorous estimate of epiplexity. So I like the area under the loss curve, so I don't want you to feel negatively about it. I think it's a very useful heuristic, and it's one of the practical things you can do to get some sense of epiplexity. And as long as like the true differences in epiplexity between different data sources is smaller than or larger than your error bars in measuring epiplexity, then this is still useful. And sources of error in measuring epiplexity could come from some suboptimal hyperparameter sweep or this area under the loss curve heuristic or other things. But like to push against the area under the loss curve, like in order to derive this, we needed to assume things like symmetry of information, which we're assuming doesn't hold when you have time constraints and things like this. It's also basically taking a difference of two upper bounds, which in itself is not going to be an upper bound of the model size, et cetera. So it's really just a heuristic that can kind of get you started in approximating epiplexity. We have a much more rigorous estimate, which we introduced, called sequential coding, which is based on something called relative entropy coding. And it instead takes like an expected KL divergence between a teacher model and a student model. And it provides much higher fidelity estimates of epiplexity. It's slightly more expensive than this area under the loss curve, and it's harder to understand, perhaps conceptually, but we can talk about it in a bit. Okay, so now that we have this foundation and we know what epiplexity is and how we can approximate it, let's use it to kind of sort through some of these apparent paradoxes. So as we've discussed, pseudorandom numbers are deterministically generated, and They don't increase Shannon information or Kolmogorov complexity by any significant amount, but we can prove that they do increase time-bounded entropy and have low epiplexity, which is what we would want. We can also look at this empirically. So here we have three different ECA rules. Rule 15 learns very slowly. Rule 30 is pretty unpredictable from the perspective of most models. And Rule 54 will learn slowly and be predictable, but the model has to work pretty hard in order to make sensible predictions on data generated from Rule 54. So we can see the time-bounded MDL in the bottom left plot for each of these rules. So Rule 15 is in green. We see that that shoots down very quickly. This is a very learnable problem. In the middle panel, we can see that this has low epiplexity. In the right panel, we can see it also has low time-bounded entropy. For Rule 30 in red, the time-bounded MDL doesn't really change. We're not able to learn anything here. And so we have low epiplexity and we have very high time-bounded entropy in the bottom right. For Rule 54 in purple, we're learning slowly, but we are learning something that helps the model make predictions. And so we see that as we increase compute, the epiplexity increases and the time-bounded entropy decreases. These thin lines are just hyperparameter sweeps to try to find points on this frontier for optimal time-bounded MDL. So the second paradox was that information is independent of ordering. We can show theoretically that time-bounded entropy does not satisfy the symmetry of information. So if we have transformations like one-way functions in cryptography, which are computationally easy to evaluate in one direction, but very computationally expensive to invert, we can show that when we apply those transformations, say to X, going from Y to X will provide more information than going from X to Y when measuring time-bounded entropy. And this also suggests to us things like data format would be able to change the accessible information when we have a computationally bounded learner. We can, again, explore this empirically as well. So we can look at predicting the outputs of Rule 30 in forward and reverse. And so this is conjectured to be essentially like a one-way function. And we can show that there's much higher time-bounded entropy when we try to predict in reverse. We can also look at things like orderings for games. So we can imagine having chess moves and the configuration of a chess board. So we could try to predict the board from the moves, which is kind of trivial, or the moves from the board, which certainly is not trivial. This reverse ordering has much higher epiplexity. And we find that the corresponding representation is much more recyclable in various different downstream settings. So you can apply the model which was trained to predict the moves from the board to things like centi-pawn chess evaluation puzzles, and you'll get better performance. Paradox 3, that likelihood learning is just distribution matching. That in expectation, we can't hope to go beyond the process that generated the data that we're training on. There are various different ways to explore this, and we do consider multiples. So there's this quote from Ilya Sutskever. I thought of it as a recent quote, but I guess like 2019 isn't very recent and a lot has changed since then. But he was asked in an interview around then why we should care about next word prediction, why that's interesting and why it would be associated with intelligence. And he said something like, imagine you're reading a mystery, a murder mystery, and the last sentence of the book is the murderer is blank. If the model is able to predict blank with a high degree of accuracy, then presumably it's been able to understand something non-trivial about the book, and that ought to be associated with intelligence. You can actually repurpose this quote to motivate this idea that likelihood modeling is not just distribution matching when you have computational constraints, when you think about induction. So the induction that we have to do in trying to figure out who the murderer is from reading the book is very different than the induction that the author would have done in writing the book. So the author might have just decided, like, Bob's the murderer before they'd written most of the book. And like, now let me plant a few clues to make people think that Bob might be the murderer. So induction really does depend on the observer. And so as a simulation of something like this, we created a binary string, and then we had a function which acted on that string to create some kind of output, f. And then we showed the model a copy of the initial string before the function had acted on it, but with a certain number of masked bits. And then the learner had to predict what is going to be the output of this function. And so the more bits that we mask, the harder this problem is going to be. And actually, the more epiplexity that the model is going to extract from the data. And so this is something that we can measure as a function of computation here. And this is also an example of how the induction that the model is having to do in this instance is different than what happened from the generative process for creating the data. We also looked at this question of emergence from the perspective of different architectures on this ECA Rule 54. So this is the rule that is fairly sophisticated, but still learnable. In this instance, we're looking at looped and non-looped transformers. And we see that beyond a certain threshold of compute, the looped transformer time-bounded MDL just shoots down to almost zero. And so what's happened here is that beyond a certain compute threshold, the loop transformer is able to basically brute force unroll these autoregressive states and make predictions. So it actually is able to like understand what are the rules that like are generating this data. So this is an example, like I think it's very analogous to lots of like problems that we face in ML, and we will consider some like real problems in a moment. But like there are simple rules that might underlie the data that we're observing, but we're not smart enough or we don't have enough computation to figure them out. I mean, pseudorandom numbers has been kind of a running example of that, but there are many, including many of these ECA problems. And so instead what we do, since the data still does have some structure, is we latch onto this emergent structure in order to make our predictions because we're not smart enough to figure out what the generating rules actually were. And so in the case of elementary cellular automata, you can see floaters on the screen and things like that that you could use to predict what the next states would look like. And in fact, if you were just looking at the outputs of these rules, that's exactly what we would do. We wouldn't like be, I doubt we would be able to reverse engineer, okay, this is the actual rule that's being used to generate this data. If we could do that, then we would make great in distribution predictions. Instead, we would just look at it and try to see, okay, is there some sort of emergent structure that we can latch onto to be able to make semi-sensible predictions as we predict the states ahead. And so that's what these models are doing. And with this looped transformer, eventually, beyond some like pretty large compute threshold, it actually is able to reverse engineer the generative process for the data. Its epiplexity shoots down, and it'll be good at in-distribution predictions. I suspect that representation won't be good at very much else. Just before that compute threshold, the non-looped transformer has actually very high epiplexity. And so it's latching onto a lot of this emergent structure in order to make these predictions. And so I'll come back to this in a moment, but I would suspect in practice that for most problems that we encounter, epiplexity would be increasing with computation. But at some point, like beyond some like extraordinary compute threshold, maybe the model would just like reverse engineer the laws of physics or something like this and actually be able to make incredible predictions with a very small description length. Okay, so now let's touch on real applications.
Just a quick
Yeah.
question about this. So you have this
two-phase behavior, like with the coffee you were describing, right? That's what we see on the right here, if I'm not mistaken. I guess that's not measurable or visible everywhere. And some of your other experiments, you started with high epiplexity and then it just dropped. Is that true?
I would say epiplexity in the other experiments was just increasing mostly. So if we look at these curves, for example, for purple, it's just kind of going up. Here it kind of goes up and down, but it's basically kind of goes from nothing to something. So I would say.
I guess I was thinking of the loss curves we were discussing. I guess the loss, looking at the loss, gives good intuition, but it's not everything.
That's right.
Okay. I
It's
see.
not a perfect measure of
I see.
epiplexity. Yeah.
I see. Thank you.
So we do actually, come back to this in a moment. So we'll expand on it a bit. But so one clear application of epiplexity is to actually use it to do data selection, because our goal is perhaps better out of distribution generalization. And this is just increasingly the way that machine learning is headed, right? Before, we were sometimes in a setting where we have some training points, which are presumably drawn from the distribution, close to the distribution we want to make predictions for, and then we can apply all this theoretical machinery to reasoning about model selection, et cetera. But that's just not really how we're using our models in practice anymore. We're training on all sorts of heterogeneous data sources, and we don't even anticipate in many cases how these models are going to be applied in downstream settings. And then we have results like LLMs for time series and crystals, et cetera, where they're just these profound distribution shifts. And so I think it's becoming increasingly important to have a theory for data selection, and also a theory that explains like emergent phenomena and the role of deterministic transformations, et cetera. And so we can try to operationalize this. Here, first, we wanted to understand this question of why does language data tend to lead to more transferable representations than image data? And so I love working with vision, et cetera, but it just has been something we've observed. So like those examples I gave were LLMs trained on next word prediction, then applied in quite different seeming settings. We can measure the epiplexity of different sources of data and actually see that it's much higher for language data than for vision data. Here we actually use this very careful sequential coding approach to doing the measurements as well. This is kind of intuitive because language is already representing a pretty distilled form of information, whereas like raw pixels in an image, et cetera, are not very compressed. And indeed, we see that different ways of tokenizing images could lead to different levels of epiplexity. So if you look at these VQ representations, for example, they have higher epiplexity than just natural representations. We also looked at curriculum learning and data selection procedures and tried to understand how they were outperforming just selecting natural batches of data. So there's this experiment where you have a data set called the pile, and it's got all sorts of different data sources like archive and GitHub, et cetera, and then a bunch of different downstream tasks. And there are various different procedures that have been developed to try to balance like which data sources that you're training on, et cetera, adaptively. And we can measure the epiplexity of what the model is learning as it does this. And we can show that even though it has higher ERM, it is extracting more epiplexity from the data that it's choosing. And then that's leading to better downstream generalization. We can think about estimating epiplexity from scaling law assumptions. So there might be this question of like, how do we really operationalize something like this area under the loss curve and compute it efficiently and make it really practical? Well, you could actually estimate it by using scaling law curves. And this is something we did. So using these scaling law assumptions and area under the loss, we estimated epiplexity and time-bounded entropy for a variety of problems with a budget of about 10 to the 25 flops. So this was equivalent to the training compute used for 70 billion parameter llama 3. Yeah, as I mentioned, found language data has the highest epiplexity, image data the least, generally. We can plug in these asymptotics to try to see what happens to epiplexity as we increase compute, and it generally predicts that it will keep increasing. But there's a caveat. I don't think it's a practical caveat, but as I mentioned, beyond some extraordinary level of compute, you might actually just be able to reverse the generative process for the universe or something like this, and maybe it has a short description length. Yeah, this is just expanding a bit on these curriculum learning experiments. I think that this is a nice way of going beyond the heuristics that people are currently using to reason about data selection. So people often talk about like diversity and quality and stuff like this, but it's kind of hard to know what you actually mean by those things. Now we actually have something that we can quantify and we can intuitively understand is, okay, this is like the structure that the model is learning from the data. And we're actually in the process of operationalizing epiplexity for data selection and data generation. So at the end of the Epiplexity paper, we show that like existing procedures are selecting for data with higher epiplexity, but then there's this question of like, could you actually directly try to select for high epiplexity data, and how would that perform relative to these procedures? And could you even go beyond that and use epiplexity to not just select data, but to synthesize data? So could you start with something like a pre-trained LLM and then develop RL procedures that would generate synthetic data that would have high epiplexity for that model in an online setting? And so that's something that we've been looking into, and the results are actually very exciting. Okay, so in short, by reasoning about the role of computation and by trying to target useful information instead of just any information, we can start to make sense of the tension between what seems to be prescribed in classical information theory and learning theory and what we're observing in modern AI research. Things like the data processing inequality are often thrown around to reason about things like, oh, what happens when the whole internet is just AI slop and we're training these models on this data? Like, will everything blow up? You know, that will probably not be a good situation, but the data processing inequality doesn't say anything about it, actually, from the perspective of this paper in Epiplexity. You can also sort of understand why ordering and so on are important as soon as you impose computational constraints and target specific types of information. Epiplexity is measuring the structural content that can be extracted by a learner that is computationally constrained. And even though we want to choose models that are good compressors of data, I would argue that we want to show those models data that leads the model to being very incompressible. And this is really just scratching the surface, I think, of what's possible when we think in these terms, in terms of like how we can synthesize useful data and how we ought to reason about like the value of data towards out of distribution generalization. Before this project, I had also gotten increasingly excited about trying to understand to what extent could we build universal learners. So I have a number of works on generalization bounds and reasoning about things like no free lunch theorems. And over time, I became very opposed to the idea of no free lunch theorems having any practical relevance in model construction and machine learning. And so I remember at the beginning of my PhD, I was really excited about automating kernel selection and kernel learning. And when I gave talks about those things, there would usually be like some learning theorist in the audience who would raise their hand and be like, well, what was your approach specifically designed to solve? Because we know from the no free lunch theorems that like it can't be good at everything. So like what problem was this intended to be constructed for? And I think at the time, what I said probably would have pleased them more than what I would say now, which is I just think the no free lunch theorems are irrelevant because the world is drawn from a small corner of all possible data sets. So the common understanding of the no free lunch theorems is that every model is equally good in expectation over all problems drawn uniformly from a distribution over all problems. The real world is not drawn from such a distribution. And actually, structure between the different problems that we're studying could be shared to a surprisingly large extent, especially at a certain level of abstraction. So it could be, and this would be the contention of people who champion Solomonov induction, et cetera, that the world is drawn from this thing called a Solomonov prior, which can represent every possible program, but has exponentially stronger weights for simple compressible programs. And so it could be that compressibility is really what ties a lot of things together. And this is something I've been excited about from the perspective of model construction. And now it's something I'm very interested in from the perspective of data selection and data generation. I think there is this question about how universal our models can actually be. So I think the no free lunch theorem doesn't say much about it, but we don't really know the answer to this question. And I think we're going to find out over time. And we are starting to find out that there's been this kind of confluence of models from more specialized learners like handcrafted feature engineering to modality-specific neural network architectures like convnets for vision, recurrent nets for sequences, et cetera, to kind of transformers for everything. And so, yeah, we'll see where it goes. Thank you.
Fascinating talk. Thank you so much. I wanted to probe you a little bit more on the data generation side of things because I think that's fascinating, and see if the algorithm used in the Suskever quote can carry a little bit more, right?
Mhm.
So in that particular comparison, yeah, like you're making a difference between the writer of the rule and the and sort of the model that learns that rule.
Mhm.
So is it useful to think about this process potentially as an adversarial process where you might want when I write a novel, I want to have clues that are not easy to figure out, but once I know the answer, everything makes sense, right? Or like, is there a way to operationalize that almost like a GAN for some?
Yeah, think about it like if you're watching a good mystery or House or something like that, like usually at the beginning of the show, they have some guess, like, oh, this person has whatever. I think it's a meme. I forget what it is, like syphilis or something. I don't know. It's like, imagine that had actually been the answer. It's like, oh yeah, like this guy was right, and it was just like that obvious. Well, that wouldn't be very interesting because like we wouldn't necessarily have a lot of confidence in that doctor and being able to solve like other kind of hard cases. Whereas like if the answer actually really was quite sophisticated, but there were sensible clues in the story that would enable you to figure out what the real answer was, then probably we would have a lot of confidence that, okay, this person probably can handle other interesting problems. And so I think that might actually be a good analogy. In some sense, we want the data to make the model work very hard, but at the end, once the model has done that work, hopefully it's able to make sensible predictions on that data. And if that's the case, there's a better chance that we can then use that model in other downstream settings.
Okay, one more question, then I'll stop. Many problems in statistics are computation bound, and they have different lower bounds depending on your amount of available computation, but we have not explored that sufficiently, in my opinion. So some of my favorite papers do exactly that. There's a paper by Quentin Berthet and Philippe Rigolet on the planted click problem, where they actually give computation-dependent lower bounds for that specific problem. So I was wondering if you've considered like easier to tackle more fundamental problems where computation plays an important role to see how your framework can kind of match, agree, or disagree with those classic results in a way.
I missed the first part of what you were saying. Did you have a problem in mind that you were thinking about? Or?
Can you hear me now? Hello? Okay. There's the planted click problem. You have a big graph and you hide the click somewhere and then you're trying to find it, right? It's known by now that there are different lower bounds on, it's off again, it's battery. I'll just screen.
It's okay.
Available lower bounds. Available lower bounds. For sample complexity for solving that problem, right, vary based on your available computation. So it's exactly this consideration.
Great, yeah.
Right? I have more computation available, so fewer samples would suffice.
Right.
Otherwise, I will need more samples if I cannot compute for a long time. So these people, through a different angle, through a different lens, have explored the same question. And I wonder if you're familiar with some of that work, or you think that kind of taking your framework to some of those easier to tackle problems mathematically might be meaningful to come up with new bounds or to see how they compare against existing bounds, I guess.
Absolutely. Yeah, I think that would be very interesting. We're currently looking at how to use sequential coding to get much tighter generalization bounds and to understand things like why larger models might be better compressors of data. So one thing I really like about like the frequential/requential approach to compression is instead of trying to directly compress model parameters, you're using the dynamics of training to understand implied compression. And this is very useful if you're working with really huge models, because one thing we've noticed, and something that I've observed quite a lot in some of my prior work, was that larger models tend to find better compressions of the data. And I don't think this is necessarily that broadly internalized. Like, I think possibly people assume that large models just trained on more data are going to work well because they're more flexible, et cetera, and they can capture more nuance or something. But actually, they also tend to find simpler solutions that might be possible to represent using smaller models, but just aren't discovered by those models when trained on the same data. So there's this question of why does that happen? Why does scale seem to instill a simplicity bias? And so this is something that we're actually looking at from the perspective of sequential coding in trying to get like better generalization bounds, even if you just have a fixed data set and you're not considering the scaling law regime and you're just scaling like the size of the model. And it seems like this is something that you might be able to do. And so I think there's a lot of analysis that could be very interesting to look into. And in terms of like problems like this, yeah, I'd love for you and anyone to send me any pointers. And I think it'd be very interesting to think about this more.
Hi, thank you for the talk. So perplexity is a very, yes, not perplexity.
Epiplexity.
Epiplexity is a new concept for me. And so I wanted to ask maybe more of a clarification question in terms of maybe putting this in terms that are a little closer to what I understand. So I'm thinking of the case of language and say hypothesizing that we have some kind of generative model that produces language. What would be the relationship in the event that between the actual generative model that produced the language and the data that we have? So say we were able to estimate somehow the actual true model, what would we expect to see in terms of epiplexity in that case? Or is it only applicable in the context where we can't necessarily estimate that true generative model, but we're trying to get somewhere close to it?
Yeah, it's a great question. And so one of the intuitions behind epiplexity is this idea that we can't often in practice reverse engineer the generative process for our data. And in some cases, not always, that can even be a blessing, because in order to make predictions, we then have to latch onto emergent structure that could be very useful. So if we think about this example of AlphaZero, the description length of that system is very small. And then we just have this training process that involves deterministic transformations, including pseudorandom numbers, et cetera. And so if we have unbounded compute, actually what's happening seems very trivial. But as soon as we have computational constraints, the model actually has to use this emergent structure to learn something that is going to be useful and recyclable beyond that distribution. And so it could be that actually in some cases, reverse engineering the generative process for the data is not what we want in terms of broader downstream generalization. And maybe the ECA problem is another example of that, where like the looped transformer was able to actually brute force unroll the evolution of these states and make really great predictions. And then suddenly its epiplexity shot way down. I wouldn't necessarily expect that model then to be useful in other settings, like we've seen in neural cellular automata, et cetera. And so we can understand, I guess, to some extent, why we see these emergent behaviors once we have computational constraints. And to some extent, why computational constraints can even be useful if we care about generalizing to other settings beyond the setting that we're training on. Yeah, I would say that's how epiplexity relates to understanding whether we want to reverse engineer the generative process or not. If we had unbounded computation, then these definitions would revert to things like Shannon information, and you would get the same sort of results.
Okay, thank you.
Do you think you can adapt the definition to in-context learning? And
To
if
what?
so, to in-context learning?
Mhm.
And if so, what will be an heuristic to compute epiplexity?
So if I heard the question correctly, you're saying, could we adapt the definition to in-context learning? And if so, how would we estimate epiplexity?
Yeah.
So it's a great question. It's something I'm thinking about, but I don't necessarily feel prepared to give a great answer to it yet. I think the answer is yes, but it's like there's a lot of nuance there in how we want to do this well. And so, yeah, I'd be happy to chat about it offline.
Okay, there were a few questions online that I want to get to. We'll see if they could unmute. Yeah, Brendan, do you want to unmute and ask your question?
Sure. Thanks, Eric. Thanks, Andrew, for the great talk. Do you have any idea what implications would be for a potential proof of non-existence for one-way functions on Epiplexity? Thanks.
There's
a lot of time-bounded entropy in this question. I like it.
Sorry, I don't know if it's audio on your
Maybe
end,
we can
but
just
yeah,
read the question.
we
in
get
the
a lot of
chat.
feedback. Maybe I'll just read it. Yeah. What ramifications would OWF non-existence have on the theory of epiplexity? I don't know what OWF.
One-way function non-existence have on the theory of epiplexity. I guess none. One-way functions are just a way of exemplifying this idea that the symmetry of information doesn't really hold once we have computational constraints. So one-way functions demonstrate this quite naturally because they're hard to computationally invert, but easy to evaluate. But there are other examples of this that don't have to be one-way functions. And so I think they're nice pedagogically, but the intuition behind epiplexity doesn't really, or the formal definition doesn't really hinge on the existence of one-way functions.
Then maybe another question online. If a structure is not extractable by a one-pass transformer, but becomes extractable after several refinement loops, would you say the data has higher epiplexity for the looped observer or lower time-bounded entropy under that observer?
I would say both. Yeah, I would say that. Yeah.
Yeah, thanks. Super interesting. I was wondering, Shannon information and Kolmogorov complexity have a nice property, namely that they are unique up to some constant, right? Like this suggests that we have an axiomatic understanding in there, and they are the right definition. Do you have something like this, or can you conjecture of a uniqueness property for epiplexity?
Yeah, I think it would hold as well in the same way as it would for Shannon entropy. Yeah, I think it would.
Hi, Andrew. Quick question on, or rather clarification question on the notion of epiplexity. So you said that epiplexity could be seen as the amount of bits that's being transferred from the available data to the model. Would you say that that's a correct way to describe it?
Sure.
Okay. And so you said that this theory could serve as a way to guide data selection in such a way that you would like to maximize epiplexity. So you'd like to maximize the amount of information that's being transferred to the model. But that seems like also one of the things that in machine learning we naively wants to avoid is to memorize essentially the whole data available at training. And so this seems like opposite goal. In one way, we're trying to prevent memorizations, which is the situations where all the training data has been transferred in the model, because the model is just like memorizing all the data available. And here you're saying that instead we should maximize epiplexity. So yeah,
it's a great question, and there's a lot of nuance, I think, associated with understanding the distinction between memorization and something like epiplexity. So if the model is memorizing, the short answer is it wouldn't have high epiplexity, it would have high time-bounded entropy, because the model has to make good out-of-sample predictions. And so if you're memorizing, you're not really going to be doing that. And so you're going to end up paying for that with high time-bounded entropy in that case. And so in cases where you have to memorize, you actually don't have high epiplexity. You want the model to be you want basically the predictable part of the data to have as much information as possible. Pseudo-random numbers would be an example where everything is kind of unpredictable if you're computationally constrained. And so again, you would have to sort of memorize to fit the training data, but you would have high time-bounded entropy and low epiplexity. So any kind of memorization scenario would not have high epiplexity. It would have to be more a case where, for first you find the optimal time-bounded MDL model. And so this means it has, like, of the models you're considering, good out-of-sample predictions on that data distribution. And then you want, like, the maximum number of bits needed to represent that model, the data that will lead to the maximum number of bits needed to represent that model. This is, I think, a good principle for reasoning about how we could build representations that could be more generically applicable, but it's not a guarantee also of generalization in a particular downstream setting. So it depends on whether that structure is actually relevant to the problem that you're considering. However, in response to your question, I would say that, yeah, this is not trying to prescribe that we should use models that are overfitting the data or needing to memorize. Instead, it's prescribing that we should show a good model data that will make that model work hard in order to ultimately make good predictions on points from that data distribution. Yep.
Super, super interesting stuff. Thank you so much.
Thank you.
I was just wondering if, to have a predictive theory of epiplexity explaining good out of distribution behavior, you alluded to heterogeneous data as well, but I wonder if that's a key part of the puzzle. And what I mean by this is, as you alluded to, we generally train on data coming from multiple different distributions, but with a lot of invariances. Like, these distributions will share a lot in common, but there will be sort of these sparse shifts across the distributions. And I wonder if this sort of notion of time-bounded compute, maybe encourages models to pick up the invariance. And it just so happens that in our universe, we've gotten lucky. A lot of out-of-distribution tasks will also have those same invariances.
Yeah.
And so, like, together, this explains maybe why simplish models trained on heterogeneous data just happen to have really nice out-of-distribution behavior.
Yeah.
About that?
It's a really interesting question. Something I'm quite interested in that's related to epiplexity is, how do we get models to do algorithm discovery? So discover algorithms that will just generalize broadly. And we considered this initially in the context of training transformers to do matrix operations. And so you represent a matrix as a sequence of numbers, and then you have a transformer predict the maximum eigenvalue or something like that. And I guess there's a question, well, why would you do that? And I think there are a lot of interesting answers to that question, given the existence of classical methods that work well for these types of problems. But just putting that aside for a moment, one thing we noticed is that when we just did this naively, so we trained the transformer on matrices drawn from a Gaussian random distribution over matrices, it would work really well at making predictions at new matrices sampled from that distribution, but it would fail profoundly on even, like, trivial matrices like the identity matrix. And it seemed to basically be doing interpolation. So if you showed it a matrix that had, like, a different decay of eigenvalues and things like this, like a Toeplitz matrix or whatever, it would instead predict, like, the decay of eigenvalues that you would expect for Gaussian random matrices. And you could do masking on the entries of these matrices and show, okay, it's predicting, like, the minimum eigenvalue you would expect from random matrix theory and so on for Gaussian random matrices. So we were interested in whether we could intervene in some way to enable it to generalize more broadly. And we found if we enriched the training data distribution significantly, so we included all sorts of different types of structured matrices, et cetera, and we added looping, but I don't think the looping was that important in this instance. Suddenly, the model could generalize very far OOD. It could generalize to matrices that were just so much different than even this richer pre-training distribution it had seen. And I think it's related to what you were saying, because if you show it enough heterogeneous data and it's a good compressor of that data, the only way it can be a good compressor is by discovering things like salient symmetries that might generalize more broadly. And so this also makes me wonder, like, should we be intervening on the objectives that we use to train these models? I don't know how successful, like, using MDL for training and so on has been. I guess people have probably thought about that, certainly related to marginal likelihood and so on. Maybe it's just computationally expensive, but I feel like this is something worth looking into. Yeah.
Yeah, we have time for maybe 2 more questions.
Hi, thanks for a nice answer. I hope I'm audible.
Sorry, we have a question inside the room.
Okay.
Hi, thanks for the presentation. I've been thinking about synthetic data generation for quite some time as well, but from an RL perspective. And I was wondering if you could expand on what you were attempting for, I think you mentioned RL4. synthetic data
Can't hear
generation.
you well, sorry.
Oh, okay. I think you were mentioning RL for synthetic data generation. Is that correct?
Synthetic data generation.
Yeah.
Yeah.
Can you expand on that as well? Because I'm really interested in that.
Right, yeah. So we'll probably post a follow-up soon, which is thinking about this a bit, but there's so much more to do. Like that is still kind of scratching the surface. So the idea is instead of only selecting data that has high epiplexity, could we possibly generate synthetic data that has high epiplexity for the model? I wasn't sure if this would work very well necessarily, because when you're selecting across natural data, you're still kind of grounded in the real world in some sense. And so it feels like there might be a better hope that the structure of that data could transfer to other settings, because it's generated from the same distribution in some broad sense. But it did actually work reasonably well. There is sort of an interesting question there. So what's your learning signal for sort of generating high epiplexity data? So you could have a reward that is based on something like this area under the loss curve or differences in loss at different time steps. And then you could develop like reinforced like procedures to try to create data from a generator model that would have high reward. And then there were some details that we found to be useful, like having a buffer of real data to sort of try to ground it in something like connected to the real world in generating this high epiplexity data. And that seemed to be very, very effective for creating synthetic data that would lead to broader downstream generalization. And so I see this as something that could possibly be combined with epiplexity for data selection. Like you could sort of select across natural sources, but then also augment this with purely synthetic data that is created to have high epiplexity. And this could lead to broader downstream generalization and more effectiveness, especially in maybe these far OOD settings where you're using things like LLMs for time series prediction, et cetera. So there's actually a lot to consider there still, like efficiently evaluating this reward and like understanding like how you can measure epiplexity at different levels of fidelity, et cetera. And so, yeah, I'm always happy to chat about those things.
And then for the last question, maybe we could go to the person who was asking online.
Mm-hmm.
Hi. Yeah, so I was my question was actually just on definition 8 itself. So I see that, it seems to capture a lot of phenomena, like emerging structure, all this stuff. But the question that I had here is, has there been any study on how does this definition work when you kind of study combinations of these quantities under different reweighting schemes?
The question is about reweighting the two terms in equation 3, I think.
Oh, it's an interesting question. I guess my instinct is I might not want to do that because like it makes sense to me to want a model that's the most compressed representation of the data. And so I don't know, maybe it could work better in some specific instances to have a reweighting. You might need to have some specific insight into the problem that you're trying to solve. As a generic recipe, I would still probably go with an equal balance of these terms, just selecting for compression. But yeah, like when you go to out of distribution generalization, it's not clear whether Occam's razor is also something you want to entirely respect. So you could look at things like spurious correlations, where like that's a great way to get in-sample predictions, and it's very compressible, but it's kind of useless in the real world. And so maybe you could consider those things also in modifying this definition.
Okay, and then with that, I think we're getting kicked out for the next event. But yeah, let's thank Andrew again.